Hello, my dear friends. This will be our first lecture. We'll look at emotion. We'll have a first look, and we will see what math equations and relations we will need mostly in this course. Here is a list of type of motions we'll be looking overall. This here would be a 1D straight line motion. This here would be a circular motion. Projectile, these would be 2D motions, and rotational motion. I will touch base on this a little bit, but that's types of motions you'll be seeing. We will start with describing the motion, and first thing we will do is to draw a motion diagram, and we can draw what a person is doing. If we take a snapshot of a motion at equal amount of times from here to here, here to there, and so on. So equal amount of times here, let's call them T at this point. And we can see how much distance this guy travels, and we can guess how it is moving. Is it moving with the constant speed? Speed each time is the same. Is it increasing speed or decreasing speed? As we see, this first guy should have a constant speed, skateboarder, because he is traveling equal amount of distance in equal amount of time. That's how we will use a motion diagram to guide us. And mind with the same fact, we're taking these pictures at equal time intervals, and we see that this lady here is moving larger and larger distances as I take a snapshot at equal amount of time difference, time intervals. That tells me she is speeding up. And similarly here, I can say this car is slowing down. So motion diagrams will be very useful activity we'll be doing. Not only motion diagrams, drawing a picture of a situation will always be helpful in understanding what is happening physically. So we'll keep doing that. We'll make models to make our pictures drawn easier, to simplify what we are seeing in the situation and understanding it. We can draw descriptive models where we describe the properties in simplest possible terms. We can draw explanatory models, explain what's happening there, predicts what will happen in the future, just like we predicted here, right? We can watch this lady 2 steps and see she's speeding up. So I can predict that if I take another picture after the same time interval, probably the distance she traveled will be larger even than the second time. We will use a very simple model called particle model. Simply what we do in particle model is to replace the object by a dot, put a dot in the center of this object, and instead of drawing the whole car here, I could just draw a dot and look at how much that dot moves in equal time intervals, and that will tell me what's happening in the motion. This is the particle model. We'll be using this. So first we'll draw in a picture. It doesn't have to be a beautiful picture, but we're going to understand situation. Then we put in some numbers. I can look at a car at different times. I can draw where the car is in the beginning and in the end, and I can draw a line taking a base of my line from a post office, for example, and call that 0 point, and then I can define a plus and minus direction. Conventionally, we usually define east to be plus, and west to be minus. And then we can define positions according to that. Instead of saying 5 miles east of post office, I can say plus 5 miles. For example, here I can, after I define my system, based on a post office or any place I can choose, I can define any position of anything according to that. If I describe my system nicely, people will understand when I say the car is at plus 4 miles that means east of the post office. The cow is at -5 miles. Looks like 6, doesn't it? -5 miles means cow is at 5 miles west of the post office. Then over the time we drop the post office and so on, and we call this base point origin. We can keep origin, and we can keep the line, and we can call that a line. We can give that line a name. Draw a line along the motion. I'm going to carry this to a little bit down here, if I can. And I'm going to call it X line. We can put the arrows, sometimes we don't. But all in all, we'll call the east plus X and west minus X. So mathematically describing, okay, something is moving along the line X. My description is that X is from east to west, and it's moving towards plus X, towards east. And always as we talk position of objects, east of something, west of something, that something is our origin, which is the post office in this case. It could be anything. Not east, west. We can do the same for north and south. So we describe the position after we understand and draw a picture, and we say, okay, let's see according to what this object is moving, and we base it according to something. It could be a building, a home, it could be a lake, a tree, anything. That's our origin. That's, my friend, is defining a coordinate system. I'm gonna also, we'll get to this soon. Not yet, but soon. The vertical position we can also define as plus and minus y. I don't want to put it on the picture because it's going to be too crowded then. But if something is moving north and south, we can define those with y. So when I say y, plus y is north, minus y is south. And there is also a base point I choose here, which is my origin. Now first we will look at 1D motion. It will be either along x, plus or minus, or along y. But once we get to 2D motions, we will see something could be moving along both. And we'll have to deal with those, and we will learn how to deal with those. So for this lady here, then I have the origin, starting point of my choice. I will also have an original time. We call these initial times and initial positions actually, and then define her position along X. She's now going towards it, east or plus X direction. And to ease my drawing, I can also use dot. Personally, I like drawing a picture, although it's going to be quite ugly, you'll see that. But I want to see the picture, and I imagine the dot is in the center of that picture, so that it helps me see in the physics better. Ever since I was a student, that's what I do. But feel free to draw the dots instead of a person or a car. It's easier, and define how it moves by showing where it is at equal amount of time. And we put time steps as well on the pictures to see how much time has passed from the beginning. Initial time here, 0 seconds. And see what's happening. Picking the initial time is also up to me. Just like I'm picking the initial position, I based on a situation, on a location I know. I can just say, okay, this person here, I'm looking at it, or the car, equal amount of distances, travel an equal amount of time up to here, then it starts decreasing. So probably this guy went constant speed for some time up to 6 seconds and then started to slow down. Or I can, or 4 seconds as we see here. Let me look more careful. Or I can say, okay, I don't care about the time of constant speed, so I just don't want to watch the guy at that point. I want to start watching the guy here. I want to see how his slowing down motion goes. Then I can set my time to 0 here. This gives us an easiness in finding the time difference, T initial and T final, because we will always set the T initial to be 0 at the time we start watching a motion. And then we took it the difference, it's always going to be T final minus T initial. Now my T final is 4 seconds here because I based my watching of this motion at the point of start where it starts, at the point where it starts decreasing speed. If I decide to watch it from the beginning, then my total time T final is 8 seconds. That's also up to me. So what we do here, simply we look at a motion, we draw a picture of it, we take a sequence of pictures over equal amount of time to understand what it is doing. We can symbolize it with points and draw the same, and then we put numbers on it to understand how that object moves. As we put numbers, we have to base our starting point to something that we call origin spatially, and define if it is going right or left or east or west, and define a time that we call initial time. Now before we move on further, we'll get back to it again. I want to touch base on some math reviews. We'll review units quickly here, scientific notations, unit conversion, trigonometry, graphs, and scalars and vectors. These are our main mathematical applications we will use, and it will be useful to review them first. I know it's going to be a lot of information, and then we'll get back to them as we use them, and we'll have this vague memory of what everything is, and then settle it down with questions. First thing is scientific notation. Sometimes we have a very large number, very, very large, significantly greater than 10. Sometimes we have a very small number, significantly less than 1, and writing them is hard. So we want to use a simplified notation. For example, this value, 6,370,000 meters, is about the diameter of the Earth. And I can write it this way, but I'll have to write down all these numbers. So how can I simplify this? To simplify a very large number and write it as in scientific format is to start from the very end of the number and go back by one numbers, okay, until I reach to a point where I have only one number left. And then I write down that number. Here we used 2 decimals. This is very good approximation generally. I'm going to ask you to use 2 decimals. Significant figures are a little bit more confusing, but we have 2 decimals here. I'm going to focus on that. And we write a number until we get to a number that will be smaller than 10. So that number should be between 1 to 9. And it should be smaller than 10. And then write that number and then say times. And I count how many steps I moved backward. 1, 2, 3, 4, 5, 6 steps. It will be times 10 to 6. That means I'm multiplying this guy by 10 6 times. If I have a very small number, this number here is diameter of a red blood cell, so I'll have to write 0.0000075 meters. Even saying that is not easy. What do I do in this case is again to write it in scientific format and see it nicer and understand it better, is to start from the dot, move right direction this time until I get to a point just before the very last number. Then I write down this number here. What I have here is 7.5. There is no more decimals, so we'll say 7.5 here. And how many steps I moved in the right direction, then I'll have now 10 to minus that number. We have 6 steps here. We put 10 to minus 6. That's scientific notation. And to practice it, I want to play around with this number here. This is a nice number. I don't really have to write it in terms of scientific notation. 1879. How many different ways I can write it? Well, this is one way, right? We generally write it this way. This is not a very large or small number. But we'll just practice. So what I can do is to move one step backward and write this 187.9. Since I moved one step backward, it will be times 10 to 1. Another 1879, I can do 2 steps backward, right? 1 step, 2 steps, then it will be, and I am stopping here now, it will be 18.79. Now I move 2 steps backward, so it will be 10 to 2. And the last option would be moving 3 steps backward. Oh, not that. So here's my number again. It takes time, but I'll use a different color here. 1, 2, 3 steps. I'll stop here, very last number. So I can write this guy as 1.879 times 10 to 3 steps back. So it will be 10 to 3. I can round this 8879 to 88. I'm dropping 9. Completing that up 1 because 9 is larger than 5, right? Times 10 to 3. I could also move, oops, not that, 4 steps backward, right? I'm playing around here. I can do whatever I want. 1, 2, 3, 4. Then I'll be here. If I do that, I have to put a 0 here then. And my number will be written as 0.1879. Since I moved 4 steps backward, 10 to 4. I'm going to write and round this to 0.19, dropping 7, round it up because it's larger than 5, so 0.19 times 10 to 4. These numbers are all same. Which one looks the best is this guy here. That's the way we want to go. So I want to move backward as much as having a number that is in between 1 to 9 and then write down the 10 to power. We can do addition, multiplication, division with the power of 10 notations or scientific notation. There are rules for doing these arithmetics, but you guys will be putting them in your calculator. This page is just to give you an oversight of how they look. If I multiply and I add the powers, here I have 6 and 2. I will add them. Here as well, I multiply this guy by that and add the powers to get this 3 times 10 to 5. If I'm dividing, it's the power in the numerator minus power in the denominator. So 5 minus 3, I'll have 10 to 2. Similar here, I divide 5 by 2 here, 2.5, and then do this. I often do these in my head because they're quite easy most often. But if you put them in your calculator, set up your calculator properly, put proper parentheses, you'll get correct answers. Adding and subtracting is more tricky. We have to have the same power so we can add them. We have to rearrange or just put them in my calculator. So that's scientific notation. Often we'll have units and we'll have to do unit conversion, so I want to quickly touch base on that too. In this course, my friends, these are our units. Is this necessary? No, but I make it necessary to ease your work, so you will know that always convert whatever unit you have, convert to this, which what we call SI unit. So you are given a unit in different format, you convert to SI units. And what are they? If I have a length in SI unit, it's in meters, mass in kilograms, and time is in second. There is CGS units also. Some books uses them, in our books here and there it's used, but mainly we will stick with the SI unit. But if I go to CGS units, length will be centimeters, mass will be gram, and time will be, again, seconds. From one unit to the other, we will always have conversion factors. This table lists them here. If I have tera, it's 10 to 12. So if I have terameter, it's 10 to 12 meters. And similarly here, we might have giga, mega, kilo, centi, milli. Often we see nano, sometimes depending on the topics we're studying. Tera, giga, maybe less. But we can refer back to this table to see what is what. Always, though, questions gives us the value. We can check online how many nanometers is 1 meter, for example, and so on. But one example here, nanometer is 10 to 9. That means 1 nanometer is equal to, 10 to minus 9. So 1 nanometer is equal to 10 to minus 9 meter. That's what it means. Let's do one more. You guys are not very familiar with micro. We use mu for describing it. So 1 micrometer is equal to 10 to minus 6 meter. That's what these factors means. As I do conversions, let's look at this guy here, nanometers. I'll write this. 1 nanometer divided by 10 to minus 9 meter should be equal to 1, right? Because they are equal to each other. Or the inverse would also hold. 10 to minus 9 nanometer over 1 meter is equal to 1. So as I am converting units, either I'll multiply by this or by that, depending on if I'm converting from nanometers to meters or meters to nanometers. And we will decide accordingly. This example here will help us how to apply this. This is a figure of electromagnetic spectrum, simply light, and how many different light waves we have in there. And these are overall wavelengths. The question tells us the wavelength of a radio wave varies between 1.2 millimeter and 100 kilometers. What is the range in meters? So we're going to convert both of these to meters. First, let's do the millimeters. If I look at my table here, milli, 10 to 3, so this tells me 1 millimeters is equal to 10 to minus 3, again, minus 3, not 3 meters. So to convert 1.2 millimeters, I have to multiply it by either this guy over that or vice versa. And I want to get rid of millimeters, so I want to multiply it by this. 10 to minus 3 meters divided by 1 millimeters. Millimeters will cancel. And I'm going to have my result in meters. It will be 1.2 times 10 to minus 3 meters. All right. Now this is the lower end. Higher end, kilometers. I'm going to use maybe red here. Put the division. How do I convert to kilometers? I look at my table again, or my question gives it to me that 1 kilometer is equal to 10 to 3 meters, right? So 1 kilometer is equal to 10 to 3 meters. That means 1 kilometers over 10 to 3 meters is 1, or 10 to 3 meters over 1 kilometer is 1, right? And I have 100 kilometers. I'm going to multiply it by this version, 10 to 3 meters over 1 kilometers, because I want to get rid of this guy. I'm converting from kilometers to meters. I want to be left with meters. And my result will be 100 times 10 to 3 meters. I can write this in a better way. This is 100. I want a number that is smaller than 10. So I'm going to move 2 steps back. This will be 1.0 times. I went 2 steps left. So I'll add 2 to here, 10 to 5 meters. Here we practiced scientific notation plus unit conversion. So what is the range in meters? This to that. So 1.2 times 10 to minus 3 meters to 1.0 times 10 to 5 meters. Radio waves range, wavelength range. All right, this is unit conversion. We will be doing it over and over and over and over again. You guys will be experts on this, but I wanted you to get on board here. And this page nicely summarizing what we do. We are converting from miles to kilometers here. 1 mile equals to 1.609 kilometers. We can approximate this to 1.61 kilometers. I like using 2 decimals. But anyways, they use the full, more precise version of it. This tells me that 1 miles divided by 1.61 kilometers is equal to 1.61 kilometers over 1 mile. This is all equal to 1. So if I multiply my unit with that, the result will not change. Only it will change my unit to a new unit. So keep on going back to this page and this equation to this question to review. I'm also going to post the annotated version of this lecture, so you guys will have solutions there. One more thing I want to mention here. This is very useful, not necessary, about units and unit conversions. This is also called dimensional analysis. Too technical, I don't know, that's, but dimensional analysis. Very shortly, it's simply checking units in a question quickly to see if I'm solving the question correctly. Quite often it's useful. Sometimes it's confusing. Skip it if it confuses you, but sometimes quickly you can check the units to see if your solution is right. Units works like math. So if I'm dividing units by units, that the new units will be unit over unit. What does that mean? Distance is in meters. This is, I'm looking at SI units here. Remember, meters, kilograms, and seconds. Velocity is distance over time. So whatever number I have for distance, I divide by time. That will be my velocity. And as I do this division, I also divide meters by second, and unit will be meters per second. I can also write this like that, but often we write it in a nicer looking format. Time is second, Acceleration is velocity over time. Now I got the velocity unit here, meters per second, right? Velocity is meters per second. I divide by time, unit second, I'll have meters per second per second. What is this telling me is that how much velocities change in each second. That's the description of acceleration, actually. We'll get to this. I should show it this way, but it doesn't look really nice. So we usually say this meters per second squared to make it nicer looking. If I have a question, I am putting an equation to solve it, I can quickly check the units to see if I am doing this thing right. In simpler cases, again, it works. Maybe it's harder for harder cases, but I'm going to move this guy here a little bit. So this question is telling us which equations are the units on the left side consistent with the units on the right side. And my pencil here. And my favorite blue color, x equals vt. What I do is simply, I'm going to write this a bit larger first. Put in the units and cancel what cancels to see if left unit is equal to right unit. I have meters on the left, I have meters per second, and second from time, meters. Good. The second one, I'm going to do the same. I'm putting in the units. Perhaps it will not. Oh, well, let's put in the values. Velocity is equal acceleration times the time plus 1/2 acceleration time cube. Units: meters per second squared times second. Here I can keep the number. In this case, I'm doing the dimensional analysis. The number doesn't matter. I'm only looking at if the units are in agreement, right? But I can leave it to. So let's see what's happening here. Left-hand side, meters per second. First term is good, meters per second. If I'm adding units, the final unit will be one of the units as I add them. So if this is meters per second, I'm good. Plus meters per second here, second term as well, I'll be good. Let's see if I'm getting that. If I have second cube here, 3 goes away, this guy goes away, I have meters plus second. That is not possible. I cannot add meters per second, not plus, sorry, meters times second. That means there is an error with my question. Again, don't worry about the number here. We're not solving this question. We're just looking at dimensional if we are doing it right by looking at the units. Check the last one. You should get meters on the left and on the right meters plus meters. So it will be correct. If I'm adding again meters plus meters, the resultant unit will be meters. If this is 1 meters plus 1 meters, it's 2 meters and so on. If I'm multiplying though, that's a different issue. It will be meters squared. So keep that in mind. Okay, that's enough confusion. We should move on. Trigonometry. This page is summarizing all the trigonometry you will need here. Right triangles. You guys want to be friendly with this. Review your basic geometry knowledge from high school and middle school. This part I am removing. It has an error and it's not really used often, but so forget about that part. And right triangle. It has a 90-degree angle and some other 2 angles. First letter, this letter here is called theta. It's a Greek letter. So hopefully you guys will be getting used to using Greek letters. We often use theta. These are alpha, beta, gamma, Greek letters as well, used as angles. So right triangle has a 90-degree angle, another angle here, theta. And if we know the sides of this triangle, we can calculate its trigonometric functions as sine theta is equal to the side opposite to it over hypotenuse. What we call this large side is called hypotenuse. Cosine theta is adjacent side over hypotenuse. Tangent theta is opposite side over adjacent side. Simple as that. And we'll be using those to calculate values on and off. In the meantime, we can use inverse trigonometric functions to calculate the angle. If I know everything else, I can calculate the angle using sine 2 minus 1, also called arcsine. The sides I'm dividing is the same as the sides I use for my sine. H0 opposite over H hypotenuse. Same goes for cosine or tangent, whichever is easier in a question. If I know H0 and H, I'll go for sine. If I know HA and H, I'll go for cosine and so on. If I know opposite and adjacent, H0 and HA, I'll use tangent. Quite often we use tangent to find an angle, and we'll get to that. That's one thing. Well, two things, trigonometric functions and inverse trigonometric functions. There's also one more thing here. Very often we use Pythagorean theorem. And it tells us that square of H0 plus square of HA is equal to square of H hypotenuse. And I can rearrange this to solve for hypotenuse. When I take square root of both sides, hypotenuse will be equal to H0 squared plus HA squared and square root. If I know H0 and HA, I can find hypotenuse now and then. Let's say I know H0 and H, but I don't know HA. I will rearrange my equation here. Starting from here, H squared is equal to H0 squared plus HA squared. I want to leave this guy alone. I leave it alone. Take this to the other side. It goes as minus because it's plus here. I will have rearrange, and I will have HA squared is equal to H squared minus H0 squared. I can take square roots again because I want to leave this dude alone, right? Then I will say HA is equal to square root of H squared minus HO squared. And likewise, I can find HO if I know the other two sides. Again, we'll get back to this and questions and everywhere over and over in the course. But that's for now. Let's solve this problem. This problem tells us a lakefront drops off gradually at an angle theta, as figure shows. To provide some information about the depth, a lifeguard rows straight out from the shore to a distance of 14.0 meters and drops a weight. If we didn't have this figure here, I would tell you stop at this point and draw an ugly picture, but they already draw a nice picture for us, so we don't have to draw an ugly picture. They show the guy dropping the line and 14 meters away from the shore. They show the lake dropping down nicely, and they showed us this angle here, theta. Let me make that larger. So let's keep reading now. By measuring the length of the line, the lifeguard determines the depth to be 2.25 meters. You see, as in here, we know this guy, we know that guy. A, what is the value of theta? Now I have a triangle here, my friends. Let's make that more obvious. I have the lake here. And the guy went from shore 14 meters, so there. And then I have the height, he dropped the line. And I have the lake nicely dropping down. Let me try to pull this a little bit better. And I'm going to show my angle theta again because I draw on it. This would be my angle theta. Let's put it here so it will be theta. And we're looking for that. A tells me what is theta. Okay. Now I'm looking at my triangle. I know this side. I know that side. I know opposite and adjacent, right? From this angle here, my angle of interest. So I'm gonna use tangent. I know this. Let's use a larger. Tangent theta is equal to opposite over adjacent. And I know this is my opposite and this is my adjacent. And I also know from inverse functions, I don't have to find tangent theta, I need the angle. So I'll find the angle that's tangent to -1, the same thing, opposite over adjacent. Then I'll put in my numbers and get my theta. So tangent to -1, 2.25 divided by 14.0. And that will give me an angle of about 9.13 degrees. As you put these in your calculator, make sure you set the angle to theta. Mostly we'll use angle theta. For some cases, we might need to set the angle to radians. Not theta, sorry, set angle to degrees. So that's my angle. B. What would be the depth D of the lake at a distance of 22 meters? So if I, from here, from his knowledge now, the guy said, okay, if I go 22 meters, what would be the depth D, which is shown here? And we're going to use tangent again. Now we have a larger triangle. Let me try to show it overall. Oops. Drawing is not easy. And then that, right? Let me use straight lines again so it will be better. So I have this larger triangle now. From here to there. And I'm completing it along the lake. Angle is the same. That's very important. My angle is still theta for the larger one too. Alright, so I still have theta here, and I know that theta. That is very important for me. I know that my angle theta is 9.13 degrees. What can I do is to go ahead and use tangent theta again. And it will be opposite over adjacent, so it will be D over 22 meters. I'm dropping this opposite adjacent thing, but we're better now. We know what we're doing, hopefully. And then I'm going to solve for D. Simply, I can multiply this guy by that. That's what my D will be. 22 meters times tangent 9.13. I'm going to drop degrees too soon because I will always use degrees. And I should get 3.54 meters. Alright, that's an example of how we can use trigonometry to get to a physical value. We can also use graphs to get to a physical value, and we will use graphs to get to a physical value. We'll be encountering two types of graphs, linear and nonlinear. Here is how linear graphs looks, and their equation will be in this format. Basic description is as the power of x here is 1, y as well. And as this place here, this nice takeout here nicely summarizes. The slope and intercept can be found from the equation. M is simply slope here and B is the intercept. If we make a plot of this function, intercept is where that line of plot hits the y-axis. And the slope we can find from the plot. Plot will be a straight line like in this figure back down on the left. And we can find its slope using rise over run. What we do for rise over run, pick 2 points along the line, define x and y values as x1, x2, and y1, y2, like so. And then they draw the picture on the left, or the picture of a triangle on the left, but I always draw it on the right, so I'm going to do the same here. Imagine a triangle here, okay? There is a triangle here we can put. And look at this side over here, we call this side rise. And if you look at the values, it's y2 minus y1. And look at this side here, we call this run, and it's x2 minus x1. And we use those to find the slope. It's rise over run. Maybe I'll take it over here. Probably you guys remember this from your middle school, high school, rise over run. I'll say rise over run several times, and I probably will drop it, hoping that you guys are all on board. I want to say one more thing here. If I happen to know this angle theta and not those values, I could still find the slope. No. Oh yeah, I can. As isn't tangent theta. Again, if I know what theta is, I can generally use tangent theta to find the slope. So that's the slope of a linear function. My slope could be positive if it's upward. I tell my students usually to put your pencil, and if it's shown directed upward, like an upward slope, steep hill or uphill, it's positive. And if it is downward, it's negative. If it's straight line, it's a zero slope. If it's a vertical straight line, we don't know. There's no slope here. Or it goes to infinity if you want to be more mathematical. And we won't be worrying about that a lot. Nonlinear function has powers of x and y, only x larger than 2. We have x squared here. So this is a format of a nonlinear function. We will be solving some questions, looking at some graphs, but calculations-wise, complicated calculations-wise, we will be fine. We find slope the same, rise over run, y2 minus y1 over x2 minus x1, by drawing tangent lines at points like this figure shows here. If I do that, let me emphasize this thing here. If I draw a tangent line along my nonlinear function graph, which is a curve now, as you see, it's not a straight line anymore, I will see that the tilt of the slope is changing, increasing or decreasing. So we'll be looking at this tilt sometimes. We'll say, okay, is the slope increasing here or decreasing from here to there? Slope is increasing because steepness is increasing simply. This is one thing we're going to use. Sometimes it's easy to see what is delta y, rise, right, over run, delta x, and we can use those to solve for some values. If it's not clear, we are looking at only majorly understanding how the slope is changing. The second example, here we have a different type of curve, and if we draw the lines at B, C, D, and so on, we see that the steepness is decreasing. So from here to there, we see slope is decreasing. You guys have some questions on this? You'll practice or already practiced. Because steepness is decreasing. So that's nonlinear functions. Alright, this lecture is getting long, so I'm going to make another lecture on vectors and scalars, still math review. I'll see you in the next video.